Okay, thanks a lot for the introduction. And thank you very much for the invitation to speak at the workshop. It's my pleasure to present some of the work here. Today, I will talk about defects, networks, and quantization. So this talk will be divided into two parts. It sounds, sorry. Sorry, I have some little, okay, sorry. This talk will be divided into two parts. The first part is about construction of a link invariant for links L in a three-manifold M, taking the form of a Riemann surface C times a real line. And the link invariant, I put quotation mark there, as this quantity will have some possible Walk-Crossing behavior. This construction in particular computes familiar link invariants in a new way. And moreover, it unifies that computation with the computation of frame BPS indices counting ground states with spin for certain line defects in 14 equals to series or class S. So this part of the talk will be based on some past work and also work in progress with Andy Netsky. The second part of the talk will be about exact WKB method for Schrödinger equations and higher order analogs, which arises as quantization of spectral curves in the H integrable systems associated with 14 equals to series or class S. And I should say that both parts of the talk are more or less to varying degrees related to other talks in the workshop. And I hope what I'm talking about could serve as a small supplement for all the great talks in this workshop. So how did I get into this business or these businesses? Also, motivation come from study of defects in quantum field theories from a physics point of view. So defects are a rich subject to study, and they're good as they sometimes encode lots of non-perturbative properties of the quantum field series. So for example, you could consider a line defect, which say extending along the time direction. Notable examples are Wilson-duped lines in gauge theories, and they're very important observables as, for example, they could tell you the global form of your gauge theory, and they could also be used to distinguish in different phases of your gauge theory. And one could also consider defects of higher dimensions. For example, one could consider a surface defect, which extend, say, time direction and one of the space dimensions. And notable example are Guckau-Witten like surface defect, which is defined also in a disordered way, similar to the Duped line. Namely, you define the defect by specifying the singular conditions on the backfields in the neighborhood at the defect. Alternatively, you could also write down explicitly a 2D Lagrangian and then couple the degree of freedom on the defect to the bug. For a generic quantum field series, study of defects could be, of course, interesting, but also challenging. And it could be difficult to give some universal statement for a large class of series. However, if you have some actual symmetry, for example, conformal symmetry or supersymmetry, or even better, both, then the situation is better. So one perspective which is orthogonal to what I'm talking about today is, for example, one could take an algebraic approach using bootstrap technology, and using the unitarity bound, one could say something about the OPE coefficients between, for example, back operators and defect operators. And there has been lots of recent developments in the physics community along that direction. However, today I will describe another kind of situation in a large class of a huge class, which by now probably a little bit old, series called 14 equals to series or classes. And in particular, we're considering supersymmetric line defects and surface defect in class S series. And in particular, part A of the talk is about lines, and part B of the talk could be motivated from surface defects. So let me first just say a few words about class S series. which Andy already, among others, already gave a review. I'm sorry for repeating this part. So class S series are 4D equals 2 supersymmetric series from a twisted compactification of a 62,0 series of type ADE on a Riemann surface C with appropriate decorations. The decorations could be punctures or twist lines. So it should be twist lines. If your Lie algebra has some non-trivial automorphism, you could also decorate your Riemann surface twist lines. If you take the zero error limit of C, then after compactification, you get a 4D and equals to class S series. And today, I will be focusing on the situation where the 6D Lie algebra G is GLN or SLN, and I will not include twist lines. The class S series has a subspace of vacuum called the Coulomb branch, where the low energy effective theory is some abelian gauge theory. And this Coulomb branch could be parametrized by meromorphic differentials on C of varying degrees with prescribed pole structures at, with prescribed pole structures at the location of the punctures. And the point in the Coulomb branch corresponds to a branch covering C tilde over C, where C tilde is the Seiberg-Witten curve. So how do you make a line defects in class S? Using the 6D construction, you start with a two-dimensional surface defect in 6D, extending along the time direction and wrapping some little loops out on the Riemann surface C. So by little loops, I put quotation mark here because for a complete picture, in presence of so-called irregular singularities, you would include collections of open paths, so-called laminations, and you could, in general, you could also have junctions between different paths on the Riemann surface C. But today, I will only talk about the loops on C. So geometrically, line defects L in the class S series correspond to loops L, little L on the Riemann surface C. And moreover, this line defect L also depend on C star parameter, which will also appear in the heating system side, which I will get to that soon. And it's physical labeling the preserved supercharges, and equivalently, it comes from the choice of preserved supercharges of the surface defect in 6D. And as another remark, the surface defect in 6D carries a representation of GLN, but today I will only consider the fundamental representation. So a useful way to study this line defects in class S series is deforming to a point on the Coulomb branch, and then you follow the defect into the infrared. The infrared limit of the line defects is a superposition of supersymmetric line defects in the abelian series with integer coefficients given by the so-called frame BPS indices, which have been studied by a lot of people. From a physical sense, you could think of this index as some sort of weighted index counting the lowest lying energy states in the superselection sector of the Hilbert space with a defect insertion in where the superselection sector is labeled by the infrared charge gamma. And this kind of flowing from UV to IR could be summarized as a UV-IR map for line defects, where on the left-hand side, you have a UV line in the class S, and then this zigzaggy arrow denotes deforming to some point on the Coulomb branch, and then you end up with a superposition of infrared Wilson-Duft lines with charge gamma represented by this formal variable and with coefficients given by the frame BPS indices. So one could also understand this UV-IR map geometrically, which will be important for the construction I will describe. So recall that the point in the Coulomb branch corresponds to an unfold branch covering C tilde over C, where C tilde is a Seiberg-Witten curve. So geometrically, let me recall like in the UV, the line defects correspond to some loops L on C. So there's a similar picture here in the infrared. The line defects correspond to loops L called L tilde on the covering Seiberg-Witten curve C tilde. So geometrically, I draw a schematic picture of this unfold branch covering C tilde over C, where with simple branch point. And as we said, the UV line corresponds to loops downstairs L in C, and the infrared lines correspond to loops L tilde upstairs on C tilde. So from this geometric point of view, this UVR map could be understood as a procedure which takes a loop L downstairs and then uplifting it to loops L tilde upstairs. So later, pretty soon, I will describe how to quantize this kind of geometric picture. But before that, let me make the connection to heating system as which has appeared in many other people's talk. To make the connection, we will put class S theory on circle at low energies, reduce on circle, and low energy, you get 3D equals 4 sigma model with the target space being the modular space of solutions to Hitchens equations. And this modular space is hyperkiller, so it has a full CP1 family of complex structure labeled by zeta, which is exactly also the same parameter labeling the preserved supercharges for the lines in the class S theory. So if zeta equal to 0 or equivalently zeta equals to infinity, what you have is a complex integrable system. So you have a vibration over the so-called Hitchin base identified with the 40 Coulomb branch, where the generic fibers are compacted tori correspond to choices of the Wilson-Duft lines wrapped around this compactification circle. If zeta is a C-star parameter, then this Hitchin modular space is diffeomorphic to modular space of flat GLNC connections A zeta on the Riemann surface C. So how do the line defects come into the story? One could consider wrapping the lines around the circle, then you will get a local operator in 3D. And the vibe of this kind of configuration you would expect it to be a function over the Hitchin modular space, and you could explicitly write down this function, namely it's exactly trace a holonomy of this flat GLNC connection along this little loop L in C, labeling this line defects. So this is a UV picture. In the infrared, you get a similar thing. However, instead of global functions, the web of infrared lines wrapping the circle only gives you the local double coordinates labeled by chi gamma on the Hitchin modular space or modular space of flat connections. So in this sense, this UVR map could be interpreted as a trace map, expanding trace or holonomy of a flat GLNC connection along some little loop L on C, expanding it in terms of double coordinate chi gamma with some integer coefficients where these coefficients, were defined earlier, therefore in BPS indices. And from a physical point of view, one could also refine to define a refined index, essentially counting the lowest lying states together with our spin information under the rotation group. And this refined index will depend on the fugacity Q. So this hints that there should be a quantization of the UVR map or the trace map. So in the following, I will describe how to construct this kind of quantum UVR map. But before that, we need another structure on the space of line defects, namely the line defects operator products. So physically, the line defects, as we described earlier, it extends along time direction, and it's inserted at a spatial point. And you could consider the limit where you bring the insertion points close to each other. And in a generic quantum field theory, this limit is usually singular. However, here, because of supersymmetry, this limit is non-singular. So at the collision limit, you get a new line, a product line, which is denoted simply as a product L1 and L2. And you could consider the web of this product line wrapped around a circle. And this web could be written as the product of the web of the separate two lines. So in this sense, this line operator OPE, operator products, is identified with the natural algebra of holomorphic functions on the Hitchin modular space. And this algebra structure admits quantization in terms of skin algebras. And there are many different ways to motivate it. But one really straightforward geometric way is to recall that those lines are labeled by loops L on C. If you want to quantize this algebra structure, you would like to introduce an ordering between the loops on C. So namely, instead of loops on C, you would be like to think about links in C cross a real line. So that's how the skin algebra comes into the picture. And I will define the skin algebras momentarily. And another physical point of view to understand this quantization algebra structure is to turn on omega background on a spatial R2 plane, where after you do that, the lines are going to be restricted to sig as the origin of the R2, namely their insertion point are restricted to lie on a fixed axis in space. And after you do that, the operator products are still going to be non-singular. However, they're non-commutative anymore. They're not commutative anymore. It's the two limits where you let the line approach L1 approach L2 from the left versus from the right is different because you cannot define this past L2. So anyway, so you get a non-commutative OPE. And in general, in the UV, in a generic class S series, those are, of course, described by skin algebra, but in general, it's not a simple description. However, in the infrared, there is a simple description, which also comes under the name of the so-called quantum torus algebra. So one could also, this quantum torus algebra also has really nice physical interpretation, namely, on the left-hand side, I have two infrared lines, x gamma 1 and x gamma 2, with charge gamma 1 gamma 2. If I bring them together, of course, I will get a line with charge gamma 1 plus gamma 2. However, before I bring them together, I would also have electromagnetic field sourced by the two dions with charge gamma 1 gamma 2, and there is associated angular momentum. To take care of that part, I would need to add this extra Q to the DSA pairing between gamma 1 and gamma 2 part. So anyway, so in the infrared, this kind of OPE is simpler to describe. So as we see, the spatial line defects are equipped with this kind of non-commutative algebra structure. So the quantum UVR map we're after should be a map from UV skin algebra to quantum torus algebra. Moreover, it should preserve OPE on both sides, so it should be a homomorphism. So let me describe the UV and IR skin algebra. I mean, by describe, I mean really give a definition of what I'm talking about, and then I'll describe how to construct this quantum UVR map. So the UV skin algebra is the so-called GLN Humphrey skin algebra associated with the three-manifold M, which is Riemann surface C times the real line. Or I should say this is a one-parameter limit of this Humphrey, the ordinary Humphrey skin algebra. And these UV skin algebras are generated by oriented framed links inside the three-manifold M up to isotopy modulo the skin relations, where I've written down the skin relations here, where the framing I'm using is computer framing, namely the framing vector points out of the your computer screen. And the skin relations are sort of local operations on links, namely you fix, you cut out a little bulb and then fix everything outside, fix every link configuration, etc. outside the bulb, but only modify the thing inside. And this dotted line represents the projection of this little bulb you cut out onto the computer screen. So the first relation says that change of handedness of the crossing is equivalent to Q minus Q inverse times the configuration where the crossing has been resolved. The second skin relation is a change of framing relation. And the third one says that you could delete an unknown at the cost of this factor here. In the infrared, the skin algebra is defined similarly. The skin relations are much more simpler. In particular, you see the first relation, I could directly resolve the crossing at the cost of Q or Q inverse. And however, there's some little subtlety here, which is why the infrared skin algebra is some sort of twisted GL1 skin algebra associated with the covering three-manifold. Sorry, I should say that the infrared skin algebra is associated with the covering three-manifold. What is it? So recall that we have separating curve C tilde, which is a branch covering over C. And then the covering three-manifold is simply given by the product of C tilde across the real line. And recall that C tilde, the separating curve, has, since it's a branch covering, so there will be branch point. Uplifting to the 3D, you will get a one-dimensional branching locus of this M tilde over M. And I show this projection of this one-dimensional branching locus to the computer screen represented by this orange point here. And the third skin relation, which is the actual skin relation, accounting for the twisted word here, it says that if I pull a link strand across this branch locus, I will get a minus sign here. So I'll describe to you the UV skin algebra and infrared skin algebra. And next, we would like to construct a quantum UVR map going from the left to the right. And this map has to be a homomorphism of algebras on both sides. So how do we do that? Concretely, this quantum UVR map will map links L in M, three-manifold M, to combinations of links L tilde in covering three-manifold M tilde. So essentially, you write F of L as a sum over this L tilde, which are links in the covering three-manifold M tilde, with some low polynomial coefficients, alpha L tilde. Before I very briefly tells you the construction, I would like to tell you what quantities is a quantum UVR map computing. So there are two special limits one could consider, in which case this quantum UVR map gives you something familiar. So first special case is a case where suppose my link L could be isotoped to sig at the fixed coordinate along the RH direction. So for example, this red L1 here. So namely, it just corresponds to a loop on the Riemann surface. In this case, what you get in the 4D class S theory is just the ordinary half BPS line defects. And if you run this quantum UVR map algorithm, what you get is a generating function for the frame BPS indices that we described at the beginning of the talk associated with this line defects in class S. A second special limit is a case where the link L is small. What do I mean by small? By small, I mean like you could literally put L inside some three ball. For example, just this little trivial knot here, it doesn't wrap any non-trivial cycles on the C cross R. And in this case, the quantum UVR map will compute for you this particular one parameter limit of Hornfleet polynomial. So, but in general, for generic link L inside this C cross R, one will get sort of like hybrid combination of these two special limits. So in this sense, this quantum UVR map unifies the computation of this one parameter limit of Hornfleet polynomial with the computation for the generating function for frame BPS indices for those line defects in class S. So let me just very briefly tell you about the construction. So the construction could be summarized just by one sentence, namely, you give me a link L downstairs in the three-manifold M. I would like to enumerate all possible links L tilde upstairs, and then I would associate with each of these uplifted links with some factors valued in a long polynomial in Q. So there's some physics. There's some physics consideration that goes into the construction, but I'll skip it. I will describe a little more if anyone is interested. So in the following, I will mainly just tell you how these steps go to enumerate all possible links L tilde in M tilde. So L tilde in M tilde is built from local pieces. And the first ingredient in this building on local pieces is simple to think about. Namely, if you look at locally away from branch point, and each strand of the link L will get uplifted to n strands on L tilde upstairs, one on each sheet of the covering M tilde over M. However, this simple picture, of course, needs corrections. And in the physical sense, they are coming from massive W bosons in the field equals to superior mills. But geometrically, those corrections correspond to some webs extending along the so-called BPS leaves, first introduced by Galton Moronetsky, and I will describe in the next slides. But anyway, so for the GL2 case, there will only be two places where this sort of corrections could happen. So the first case is the following. Suppose downstairs on C cross R, my link strand intersect with a certain BPS leaf, which is connected to a branch point. Then upstairs, when I build my uplifted links L tilde, I'm allowed to add a little detour going from sheet I to sheet J. The second ingredient, second correction comes from the following. Suppose downstairs, you have two link strands, but they're intersecting a same BPS leaf. Then upstairs, when I build these uplifted links, I'm allowed to add these little exchanges running on sheet I and sheet J and exchanging between the two link strands. And this is a complete story for GL2. A complete story, I mean, when you build your L tilde from the local pieces, you just group together all possible local pieces from this naive uplift and also from those corrections that you would receive. And then that's end of the story. You would already enumerated all possible links L tilde in M tilde. However, for n bigger than 2, the story is a lot more complicated. These corrections could travel along very complicated web structures, which makes the whole story in the sense that 3 is not equal to 2 plus 1. So it will make the algorithm a lot more complicated. So let me describe a little bit what are those BPS leaves so that you would use to find the corrections. So recall that given a point in Coulomb branch, we have a separate curve, which is n-fold branch covering of the Riemann surface C. And you could explicitly write it in terms of this kind of algebraic equation. There are n solutions to this equation correspond to the n sheets of the branch covering. The BPS IG leaf is defined as one-dimensional leaves on C satisfying this kind of explicit condition where lambda and lambda j are 2 of the solutions to this separating curve equation. And recall that there's this parameter zeta appearing here, which this zeta could be understood as the same zeta labeling your line defects in 4D or surface defect in 6D or Wilson lines in 5D equals to super Yang-Mills theory. So this condition could be understood as sort of like a mutually BPS condition between the Wilson lines and W bosons if you're into the 5D point of view. But anyway, so there's some explicit condition you could use and to find the BPS leaves. So what do they look like? In the GL2 case or n equals 2, the structure is very simple. So out of each branch point, you have 3 critical leaves going out of it. And they divide the neighborhood of around the branch point into 3 different regions. And then within each region, you have families of the generic BPS leaves. But when I say critical and generic, I'm distinguishing on whether or not these leaves will end at a branch point. And then, so this is a picture on C. But our 3 manifold is C cross R. So this kind of leaves are going to be uplifted to foliate your 3 manifold C cross R. In particular, at each RH coordinate, you get a copy of this. So it goes like that. For n bigger than 2, this leaf structure are a lot more difficult to describe. And in particular, for example, just take n equals 3, you will have 3 different kind of leaves. So you have IJ kind, IK kind, and JK kind. At a generic point, any generic point on C, topologically, your leaf structure will look like this. And then you could ask, what about a simple branch point? After all, you could consider simple branch point, namely only 2 sheets meet together. You could ask, how is that so much different from the n equals 2 case? So in a sense, it's not that much different. So namely, I show this picture here. You still see this 3-pronged structure here. Namely, so suppose this is an IJ branch point. So you have 3 critical IJ leaves coming out of it, and there are also generic IJ leaves labeled in green. However, on the other hand, you would also have IK and JK leaves labeled in yellow coming across the whole region. So that's made the treatment a lot more difficult to describe. And I would like to emphasize that even without considering the branch point, namely, even I just take my 3 manifold to be R3, or equivalent, I take my Riemann surface just to be R2. And on the other hand, I will take my covering 3 manifold just to be 3 disjoint unions of R3. Namely, there's no branch point, like not this kind of mess at all. Even in that case, the BPS leaves, which literally looks like this, or I redraw it here, will induce to you lots of possible places where you would have this kind of web corrections. So in this slides, I showed you a chopped up version. By chopped up, I mean, sorry, there is a little bar here. By chopped up, I mean chopped up along the RH direction. So namely, my links will become link strands, which are the blue things here. And then all the different colors of the colored structures and in between these different link strands are the web structures that you have to take into account in your construction. So I could say like there are those tree level loops. And on the other hand, Sometimes, although if you just do it randomly, this is not happening very often. However, sometimes you could have a loop structure, namely this red one here. This kind of structure always appear as one of the limiting configurations of a family of webs. So for example, this one is the outer limiting configuration where this continuous family goes from this this structure to this blue structure inside, which the blue structure does have a trait topology. And then this continuous family is parameterized by this modulus, which is the length of this little guy here. So the situation complicated, however, you could still try to enumerate all possible web corrections and combining them with this naive or simpler direct lifted local pieces, and then you will find all the possible L tildes upstairs in M tilde. And then you assign those factors, alpha L tilde. So recall that after you enumerate, we still need to associate with factors. I will not describe those factors. They're kind of a mess, but roughly speaking, for the web structures, each web here will contribute a factor which is proportional to Q minus Q inverse times some integer power, where this integer power is equal to number of legs minus number of internal vertices. And it would be very nice to give a physical interpretation of this kind of dependence of this the power with respect to the topology of the webs here. In a sense, I just say one sentence. In a sense, this kind of web structure coming from the dynamical BPS strings in the 60 series, if you uplift your whole setup to 60. And I could imagine these kind of factors somehow correspond to some indices counting the zero modes living on the BPS strings. And maybe there is some effective model you could cook up, which will give you this kind of dependence. However, it's not, this is just a dream that would be cool if that's true. Okay, so I've told you the story for R3, and you could check that you indeed get this one parameter limit of Holmes's polynomial. And let me also show you another simple example, which corresponds to the other limiting type, namely where you get the genetic function for half BPS line defects in class S series. So in this case, the physical theory SU2 is F equals to 4, and I will take my Riemann surface C to be a 4-puncture sphere, and my subroutine curve will just be a branch double covering of the 4-puncture sphere, which I draw here, where I label the punctures in blue here. Anyway, so now we are considering a link L, which when I project it down to the Riemann surface C, it becomes this little blue loop, looping around 2 of the 4 punctures in the 4-puncture sphere. So, and then we could run the quantum UVR map analysis, and then that will gives you this UVR decomposition of for this UV lines in SU2 is for F equals 4 flavors in terms of the infrared lines X gamma here. And moreover, from this expansion, you could read off the BPS states count with respect to each superselection sector labeled by the infrared charge. And most of the time, those states are just have a trivial spin. However, in certain charge sectors, you do say that, for example, in this charge sector, the BPS states are the lowest lying states from a 2-dimensional representation under the rotation group. And let me also comment that this prescription here is consistent with the positivity statement in the class algebra community, where although you would say there's a minus sign here, why that positive? By positivity, I meant it's a positivity minus Q, which goes back to my convention to define this kind of indices. So this is another check that this procedure gives you a consistent, reasonable answer. Okay, so let me just also comment on some behavior that this quantum UVR map satisfies. So as we described so far, this quantum UVR map depends on this covering 3-manifold, which is uplifted from the separation curve. So namely, depend on choice of the Coulomb branch point. If you move on the Coulomb branch, the frame BPS indices could change discontinuously. This is a so-called frame wall crossing. And the way the frame BPS indices are changing discontinuously is controlled by the Buck BPS spectrum of the 4D series. And for example, across the wall associated to a BPS hypermultiplet with charge gamma, this f of L here would jump by conjugation of the quantum dilogarithm EQ x gamma. And one could check that for at least for GL2 case, our algorithm, the quantum UVR map algorithm does reproduce you a correct jump with respect to walls associated with BPS hyper and walls associated with BPS vectors. And those are the complete story for n equals 2. However, in higher rank, for example, for GL3, there will be much more complicated walls when one could have not just BPS hyper or vector, could have higher spin multiplet. And in that case, I'm not saying it's impossible to check, but it's a lot more difficult to check whether this quantum UVR map is consistent with the frame wall crossing behavior, and we are not able to do that for higher n case. And let me just comment that the first one thing that your quantum UVR map has to produce to you the correct wall crossing behavior. On the other hand, you could study FOL before and after the jump and use that to extract information about the back BPS spectrum with spin. And that goes under the name motivic Donaldson-Thomas invariance in the math literature. Okay, so let me make an intermediate summary. I described to you a quantum UVR map or quantum trace map in the Hitchin system sense, perhaps, which embeds the GLN, hopefully skin algebra, into the quantum torus. And this map gives you a new computational hopefully polynomial, and moreover, it unified it with computational refined frame BPS indices for the line defects in class S series. And let me mention some possible interesting further directions. Although I have been mentioning these kind of directions for a while, but they're still interesting to say. So one interesting direction is to consider more general three manifold and consider this sort of this similar UVR map for line defects in 3D equals 2 series. And for example, you could consider 3D equals 2 series of class R, where the corresponding three manifold are three manifolds that admit ideal triangulation in terms of tetrahedra. And in this case, mathematically, what you would get is a map between the UV and R scheme modules. So I should say that I didn't mention earlier, which I should have, which is in the class S series or the three manifold taking the form of the Riemann surface across the real line, you not only get a scheme module, but get an algebra structure where the algebra is simply given by stacking links in this actual real line direction. And you're going to lose that in the general three manifold case. So after, you will just get a map between the UVR scheme modules. But however, you could still try to formulate this kind of thing. And what's important is to figure out, essentially to figure out what's going on within a single tetrahedron. And then you could hopefully combine that with the technology that we already developed for class S, and then try to cook up some general strategy for general three manifold. And another question one could ask is whether one, because I told you this link invariant, it's not really invariant, namely it depends on the choice of the Coulomb branch point. And you could ask whether one could somehow cook up some wall cross invariant out of this invariant so that it could actually become an invariant. And so that's another interesting to think about. And there's one more thing, which I think I'll just say in words. So as in many other quantization stories, you know something interesting will happen if you take your deformation parameter Q to be a say nth root of unity. And it's also similar story here. If you take Q to be an nth root of unity, your skin algebras, both on the UV and R, have a large center. And it is so large that it is isomorphic to the space of functions, holomorphic functions on the corresponding modular space of flat connections. And one could also check this kind of statement by doing space computations, and that serves another consistent check for this quantum UVR maps. And moreover, one could hope, or I should say this part of the root of unity, I should accredit this to discussions with Galton Moranetsky. So one could use this kind of large center to construct, hopefully construct a hyperholomorphic vector bundle over the Hitchin modular space. And it's expected to be some sort of higher rank generalization for the hyperholomorphic line bundle that Andy Netsky talked about in his talk, and also potential related to Teschner's construction, which I hope I will learn tomorrow and Friday. However, I don't really know the relation, so I just said it in words. Okay, so that concludes the first part of my talk. Before I move on to say something about surface defect, maybe I should pause for some quick questions about the first part, or we could postpone the questions to the end of the talk, whatever that you prefer.
Yeah, Fei, can I ask you a very quick question? Yeah. Yes, so if you could do this on S3, right, then this would be the usual setup in Ethereum. Do you think there would be some regularity? I mean, well, there should be some regularity as you go to large N, right? That's where these Color Jones or higher Jones becomes really the home free polynomial. And then this would lead to some interpretation in terms of curve counts, as we heard in Tobias's talk. But can you expect any regularity for large N?
Not at the moment. I should say that's a really interesting question that I would like a lot to make this connection. But at the moment, I should say this algorithm is kind of complicated, and we don't have like so far we still don't have. I think it's fair to say so far we still don't have a good handle on what to expect at large N. So sorry, I don't know.
Okay, great, thanks.
Thanks for the question. Okay, so now let's look at surfaces. So how do you construct surface defect in classes? You again go back to 60, and you still pick some surface defect in 60. So similar to the line defect story. However, you're going to position your surface defect differently here. Namely, you're going to put your surface defect in 60 to sit at a point on the Riemann surface C, and expanding along two directions in your 4D space-time, like this. And this kind of surface defect, a preserved 2D 2,2 supersymmetry embedded into 4D equals 2 supersymmetric algebra. And this location of the insertion point of the surface defect in 60 correspond to like a coordinate Z on the Riemann surface C, has another meaning, intrinsic meaning for the surface defect theory as a marginal carrier deformation parameter. Concretely, for this kind of surface defect, very often you would also have a UV description for series living on the surface defect in terms of some 2D 2,2 gauge linear sigma model. And this Z could be mapped as exponential of the complex Fi parameter for the U1 gauge group in this 2D gauge linear sigma model. So we see that this Riemann surface C has a double meaning here. On the one hand, it's the internal manifold that you compactify to get class S series. On the other hand, it serves as a moduli space on marginal carrier deformations for the surface defect theory. And I should say that a lot of statements in this slide and the next slides only requires the buck to be 4D equals 2 supersymmetry. So it doesn't have to come from 60 construction. And in fact, the more interesting point of view is exactly to take it from a more field theory perspective and then to study this kind of problem. So what do these surface defects become in the infrared? By infrared, I mean deforming to the Coulomb branch of the 4D equals 2 theory. As we said earlier, the 4D buck theory is described by some effective Abelian theory, and correspondingly, the surface defect has a set of massive vacua, and those vacua are going to be fibered over your 4D Coulomb branch, and they are fibered non-trivially to form some space of vacua for the coupled 2D 4D system. And moreover, on this fibration structure of the space of vacua, there's a natural one form, lambda, which I write it as xdz, because z is like the Fi parameter for the surface defect theory, where x could be physically interpreted as a wave of twisted carrier ring operator on the corresponding vacuum. And at each vacuum, no matter what's what kind of UV description you have for your surface defect in the infrared at each massive vacuum, the surface defect becomes some simple monodromy defect in the Abelian theory with some abelian Gukov-Witten parameter, and is characterized by effective twisted sphere potential. So the nice thing about this whole infrared behavior is that this vacuole structure of the coupled 2D4D system actually encodes the Bach Seiberg-Witten geometry. Concretely, the Seiberg-Witten curve could be interpreted as twisted Carré relation for the 2D 2,2 theory living on the surface defect. And this canonical one form that you could define separately using the surface defect is identified with the Seiberg-Witten differential. And geometrically, this Seiberg-Witten curve, which is a branch covering over the Riemann surface C, where each branch corresponds to a vacuum for the surface defect. And moreover, you could compute this effective twisted sphere potential by doing an integral of the Seiberg-Witten differential equivalent this kind of one form on some open paths on this covering or Seiberg-Witten curve. So this is some sort of like a classical story. It's a nice story which tells you that if you consider the vacuum structure of the coupled 2D4D system, where after you insert some two-dimensional surface defect, that structure actually tells you the Bach Seiberg-Witten geometry. So one could ask whether one could use this kind of picture to quantize Seiberg-Witten curve. And what do I mean by quantize Seiberg-Witten curve? So by quantization, I mean quantization in the sense of algebraic curve. So for example, you consider Seiberg-Witten curve of sums for d equals 2 theory, which is written as this algebraic question. And I could try to promote X and Z, interpreted as momentum and position coordinate to Heisenberg operators. And then in position representation, you will get the following Schrödinger equation. And I should say that you would expect subtleties would appear in this business. So for example, you could get, for given a classical curve, you could have different kinds of quantization, which all reduces to the original classical curve if you take h bar goes to 0 limit. However, there are distinct quantum curve or distinct Schrödinger equations. So there's a question of whether or not there is a canonical one you could choose. So one way to think about this canonical one is to turn on the Nekrasov-Saakashvili limit of omega background along the surface defect. And that will quantize your Seiberg-Witten curve into a Schrödinger operator or higher rank opers. And this kind of this business has been studied more or less recently by these people. And there's actual ingredients in this quantization procedure, namely, you could extract this wave function psi here from the surface defect partition function in the omega background. Why do I say extract? So concretely, what you do is not directly take the Nekrasov-Saakashvili limit, but you turn the full omega background, compute the surface defect partition function, and then you take the NS limit. And when you do that, of course, your partition function will receive some singular contribution from the Bach. So that's the original story of Nekrasov-Saakashvili. If you factor out that singular contribution, you get some regular part. The regular part sort of correspond to the wave function psi here. So I wrote two remarks here. I think I wanted to say the first remark is, so first of all, this omega deformation gives you a canonical way to obtain this quantization of Seiberg-Witten curve. And I should say another way to do it, which is related to this kind of thing, is in the world of AGT, where the insertion of surface defect in 4D corresponds to insertion of some degenerate field on the Lua side or double algebra side. And then in that sense, this kind of differential equation comes from the null relation in the degenerate word module. So there have been lots of work done, I think mostly in rank 1, but also in higher rank to go through AGT to derive this canonical quantization. And I apologize that I didn't put those kind of reference here. And there's another thing is which will relates to the conformal limit that Andy Netsky talked about in his talk. So namely, what is this? This is like a rank 1 oper. So one could imagine to be able to derive this oper by doing a careful analysis of the conformal limit for the Hitchin-Moduli space defined on the Riemann surface, which correspond to the construction of this 4D equals 2 theory. And as far as I know, I don't know the current status, that kind of mass kind of consideration is not very well understood, in particular in presence of irregular singularities. So, but again, so you could also do it do that kind of procedure there. And it's a complete mystery for me that doing the conformal limit would be able to derive to you the same kind of canonical quantization as say from the gauge theory point of view. And if anyone knows why or want to discuss about that, I would be very happy. Okay, so how do we study this Schrödinger equation? So we'll use the method which appeared in the title of the workshop, the exact WKB. So we make this kind of WKB on that and substitute it to Schrödinger equation, where this lambda here has to obey the so-called Riccati equation. And one could solve this Riccati equation formally by building a formal series solution in powers of h bar. At order h bar to the 0, one would just get classical separating curve. In this case, there are two branches labeled by the plus minus branch cut. And once you make this choice, all the higher order coefficients in this formal series solution is completely fixed. So I listed the first couple orders. And once you get this formal solution lambda, you substitute back to your WKB on that, and then you get two formal solutions to the Schrödinger equation as series in h bar. And they're really formal solutions, or they're asymptotic series in h bar, particularly they're not functions in h bar. So what one could do is to do Brouwer summation to produce to you some actual functions. And it turns out one cannot do that for every values of z. One can only do so away from the so-called Stokes curves. And I show you some sort of local picture of the Stokes curve here. You can draw this kind of Stokes curve using this kind of criteria, which is similar, and it's not a coincidence, which is similar to the criteria to find the BPS leaves in the first part of my talk, where lambda and lambda j in the WKB business correspond to the two formal solutions to the zeroth order Riccati equation. So what's the structure of Stokes curve? So starting from a branch point, you have three Stokes curves coming out of it, and they globally they are either going to be attracted to some punctures on C, or they asymptotic. They go asymptotic to bound some annulus domain. That's the story for n equals to r for the Schrödinger case, and then. So you have those Stokes curves, they carve out this whole Z plane into different regions. And within each region, you could do Brouwer summation and get two actual solutions. However, those solutions will jump as you go across the Stokes curve, and the jumping takes this kind of unipotent form. And one could sort of get a handle on why the Stokes curves are determined by this condition and why the jumping happens like this by doing some sort of local analysis around a simple branch point. Namely, locally, one would just be looking at an array equation where everything could be done very explicitly. In particular, you could derive this kind of unipotent jumping using the connection formula for hypergeometric functions. So that's like one nice check one can do to convince you this is a correct picture. And how do we understand this from the surface defect point of view? And the Stokes curves has appeared for a long time, actually. They're going under the name of spectral networks. And from the surface defect point of view, these curves on C, on the Riemann surface C correspond to the set of Z in C, because Z is like a Fi parameter for surface defect theory, such that there exists a BPS Ig soliton whose central charge has the same phase as the phase of H bar. So where on the one hand, you have the exact WKB analysis, you have the Stokes curve. On the other hand, physically, they're related to the BPS soliton spectrum of the surface defect that you're considering. So what are some observables you could compute in this business? One could study the so-called Walrus symbols. Those are C star valued functions in H bar. So those are actual functions in H bar labeled by one cycles of the separating curve. There are some nice properties of the Walrus symbol. The first one is the Walrus symbol. It captures the Brouwer summed quantum periods. For quantum periods, formally is defined by integral of the formal solution to the Riccati equation along the one cycle gamma of the separating curve. So it's also some asymptotic series in H bar. And if you want a function, you do Brouwer summation, and that is captured by the Walrus symbol. From the point of view of the study of the ODE, this Walrus symbol could be expressed as Walrskins of distinguished local solutions. So they're either asymptotically decaying solution as Z goes into a singularity, or their eigenvectors of the monodromy around the loop. And from the HML jet space point of view, this chi gamma H bar could be identified as spectral coordinates on a moduli space of light SL2C connections. And roughly speaking, and I'm saying that without any mathematical rigor, one could think of this chi gamma H bar as a conformal limit of the double coordinates chi gamma zeta, which Andy also described in his talk, on the HML space or moduli space of light connections. Okay, so how could we generalize this story to a higher order Schrödinger-like equations or Oper equations? For example, one could consider an nth order differential equation with n-1 potentials. Or let's just be precise. So it also happens in the first part of my talk. I distinguish between n equals 2 and n bigger than 2, but in reality, what I could do is only n equals 2 and n equals 3. Okay, the first part, there's much more distinction between equals 3 and equals 4, but less distinction here. But anyway, so we're just going to look at a third order differential equation. For example, this one here. Then you do WKB on that, so you get some sort of more complicated looking Riccati equation. And I do not know anything in math literature about this WKB analysis for higher order differential equations. I think Nikolaev have some progress made in that direction, but I don't know precisely yet. So from a physics point of view, there are still surface defect in this kind of higher rank class S here. So you could still consider to draw the soliton path or not soliton path, but the values of Z where there exists the soliton that you wanted, or to draw the spectral networks using the GMN techniques. And those are going to be expected to still be serving as a Stokes curve in this analysis of this third order differential equation. So there again, here, just as in the first part of the story, when you go from n equals 2 to n equals 3, 3 is not equal to 2 plus 1, so you get some more complicated structure. For example, you get these actual junctions where you have two Stokes curves coming and intersect at some point, but then you get a third new Stokes curve coming out of it. So the analysis is a lot more complicated. However, you could still conjecture the following picture, namely, you have those Stokes curves, they carve your Z-plane to different regions. At each region, you have 3 local solutions, which you would be able to obtain by Brouwer summing the formal solutions again for solving the Riccati equation formulae and then substituting to your WKB on that. So you have 3 actual local solutions in each region. And then as you cross the Stokes curves, those solutions again jumps in a similar unipotent manner. And then you could try to study this kind of problem. So for example, I should say, I put, there are many people studied different kinds of problems and made different progress in this field. And I will just talk about a very simple example, which is this third order differential equation understood as a quantization of separating curve for the n equals 2 SU3 superYAM-Mills, where the classical curve is realized as a triple covering on CP1 with 2 irregular singularities. So I show you a sample Stokes curve which appears in the strong coupling region of the series with 12 BPS states, and they look roughly like this. So in total, there are 16 regions. So 16 times 3 is 48. So you have 48 local solutions, and then you could study them. However, the Stokes matrices put constraints on the local solutions in neighboring regions. So you could solve a little puzzle, and in the end, the only local solutions that matters are just those 2 local solutions, which I call T and S here, where T is the exponential decaying solution as Z goes to 0 along the negative imaginary axis. S is another exponential decaying local solution where it's exponential decay as Z goes to infinity along the negative imaginary axis. And by 2, I mean not just T and S, but also their image under this monodromy action, where the monodromy is a counterclockwise monodromy around the equals 0 singularity. So then you could try to study the Brouwer symbols, and again, they're going to be expressed in terms of Wronskins of T and S and MT, MS, M inverse T and M inverse S. So you get some complicated expression. And one thing one could ask is, how do you know you're actually doing correct thing? So the first step to check is a semi-classical one. Namely, recall that the var symbol captures the bar summation of quantum periods, which means that if you take h bar goes to zero limit, log of the var symbol will admit an asymptotic expansion in terms of the quantum periods. So one could do some numerical checks by numerically solving this differential equation, and then try to check numerical values of chi gamma and compare it with a truncated quantum periods calculation. And then one finds relatively good agreement. So that's something one could feel, I don't know how one would feel about that, but anyway, so, and then there are other checks one could do, which I will just really briefly mention here. So this var symbol, it also obeys TBA-like integral equation, which Dineski also described in his talk. So it looks like this. What one could do is numerically solve these TBA equations by after specifying suitable boundary conditions, and then one could compare the values of chi gamma h bar with the value of chi gamma h bar that one produces using this Wronski's of the special local solutions. On the other hand, one could also do incident calculus. The incident calculus will resolve special quantum periods, the special A and A dual periods. And the incident calculus, h bar appears as one of the omega deformation parameters, so they're by definition exact in h bar. The incident calculus it gives a different resummation of quantum periods, and those as an exact function in h bar correspond to special Weyl symbols, the so-called Finchel-Nielsen coordinates or higher length twist coordinates, which would appear in the wake coupling region of your theory. And these kind of coordinates have been studied by many people. And I want to apologize that I forgot to add the reference by Coleman, Lange, and Techter. Of course, they have also done extensive study of the Finchel-Nielsen coordinates. And I apologize that I should have added it there. Okay, so let me summarize. I talked about two things. The first thing is about line defects in class S theory, and the corresponding mathematical quantity is a quantum UVR map, which offers you a new computational home-free polynomial, and it's unified with computational refined frame BPS indices for line defects in class S series. And then we go to the second story, where you have surface defects, and this kind of surface defect consideration has implication in the exact WKB analysis for Schrödinger equations, or interpreted as quantum separated curves of the 14=2 series. And that's all I have. Thank you, and please keep staying healthy.
Thanks very much. Is there any question? Okay, so if no question, I can see, yeah, okay. Tom, sorry, you were disappearing.
Am I here now?
You're there, yes.
Yeah, sorry, it's just, it's more of a remark than a question, actually. It's just that, so this very interesting map you have from this skein algebra to the quantum torus algebra in the first part of your talk, where certain basic elements get turned into framed DT invariants or framed BPS invariants. I mean, it reminds me a lot of the situation in maths, where the way we first define these DT invariants, we have something which is a something we call the Hall algebra, and then the difficult part of the theory is to show that there is some homomorphism from that algebra to a quantum torus. And somehow the things in the Hall algebra are very easy to write down, but then the magic is that when you apply this map, you get the DT invariants and framed DT invariants as well. And I mean, interestingly, there is some work by Fabian Heiden, which computes this whole algebra for the Fukaya category of a surface, and he gets a skein algebra. So, and there are also other interesting things in that this map depends on a choice of basically a triangulation of the surface in this rank 2 case. So a lot of the ingredients look quite similar. And I think it would be really, I mean, your talk made me realize just how interesting this map is. And it would be great if we could, you know, build an analogy with the whole algebras in mathematics, maybe.
Yeah. Thanks a lot for the remark. It is very interesting. So I don't know much about Hall algebra, but the thing is that about triangulation, indeed, in the rank 1 case or rank 2, I don't know how the counting goes, but in that case, the triangulation is indeed the same kind of data I'm using this BPS leaves in the sort of like they're dual to each other. So in higher rank case, what I described, in some special cases of the situation what I described, it's also dual to a triangulation. I didn't present that result, but we have some result also in that direction. So I agree, it would be very interesting to make more connections with similar topics in the math literature. Yeah, thanks.
Okay, let's thank Fei Yan again.
Thank you.